Hello and welcome to today's lecture. Let's continue with our discussion of the exterior differentiation operator, which acts on a differential P form and the output is a P plus 1 form. Well, the very existence of such a operator or linear map, linear differential map is a theorem, and towards this we first do some preparatory work on open sets in Rn. So what we needed was this proposition. We had defined D, and then we had defined the exterior differentiation map on differential forms on open sets in Rn, and we want to check that these properties are satisfied. So at the end of last class, I had finished proving the second property. Now let's move on to this crucial and somewhat mysterious third property. Decompose with D is 0. So let me start with that. First, let's do it for 0 forms. So remember that this D was supposed to be from omega ku to omega k plus 1 u, and here I have omega k minus 1 u. The claim was that this composition is 0. So let's start with k equals 1. So in which case I have and recall that we had defined this to be just C infinity u, just C infinity functions on u. And so if I want to check that decompose, so first what I have to do is let f belong to omega 0 u equal to C infinity u. Then I would like to check whether this is 0 or not. Well, the first, so this is d of f. Now df, the way we had defined d, this was just our usual derivative operator on functions, and so therefore this is df, this is the same as del f by del xi dxi. So when I take d of this, we have already proved the product rule in part 2. So using that I can simplify this expression. So first I take it inside the summation sign. And then note that d, so this is equal to, I'll get two terms. One is del f by del xi d of dxi plus d of del f by del xi dxi. Now, well, d of dxi is 0. This is simply because the way we had defined d, the way we had defined d was any form can be written as dai dxi, and we said that this is the same thing as dai wedge dxi. So in other words, if these ai's are constants, then automatically d of that thing is 0. So in particular, d of dxi is 0. So therefore, d df equal to, so this term goes away, and I'm left with, and as for this term here, again I use this expression, except that instead of f, now I have del f by del xi. So I'll have to use a different index when I take partial derivatives. So first let's keep this sum is over I, and then this will be over j, del by del x j of del f by del xi, and then dxj wedge. Oh, here I should put a wedge dxi. Right, and now the term inside the brackets, I'll combine these two sums. The sum, both indices vary from 1 to n, and this is just the mixed partial derivative, del squared f by del xj del xi dxj wedge dxi. So let's see why this is 0. Well, when I equals j, I get dxi wedge dxi wedge dxi, that will be 0. So we just have to consider two cases, I less than j of this expression plus I greater than j of this expression. So it's the same thing here in both brackets. Now what we do is, let's just keep the first one as it is, I less than j del squared f del xj del xi dxj wedge dxi. As for the second one, I'll interchange I and j. So it will become j greater than I del squared. I do that so that basically I want to, let's we'll see. So del squared f by del xi del xj, and here I get dxi wedge dxj. Now the point is that dxi wedge dxj is the same as, so the first term I keep as it is, the second term del xi del xj, but I interchange, I swap I and j again. I change the order of exterior product rather. So I get dxj wedge dxi, but I obtained in the process I get a minus sign. So now the summation, both the sums involve summing over I less than j. Here too it's the second one is also now I less than j. So I can write it as I less than j del squared f by del xj del xi. The second one is del squared f by del xi del xj, and then dxj wedge dxi, which is 0 since the f is smooth, its mixed partial derivatives are the same. So ultimately the fact that d composed with d is 0 boiled down to just the equality of mixed partial derivatives for a smooth function. at least for zero forms. Now let's look at any forms of any. So let k be greater than or equal to 1 now. So let's start with omega b, k form. And I want to, so we can write omega equals sigma aj dxj and this dd omega will be d of, so d omega is by definition daj wedge dxj, and so now again I plan to use so this sum is over multi-indices j. So let's I plan to use this product rule, but for that let's recall that this is, I mean this is just dxj is just shorthand notation for dxj1 dxjk. So here as usual j is the multi-index j1 jk. So well, now I'll just use this step 2 which says that I can take this the d of a product obeys a sort of Leibniz rule, except that the second term acquires a negative sign depending on the degree. Well, in this case, if one has to apply Leibniz rule, so there are k plus 1 terms here. So the first term will be, so if I do this, let's regard this as a one form. Let's regard these two as omega alpha and beta. Then I'll get d alpha wedge this plus alpha wedge d of this remaining stuff. So if I call this alpha and this as beta j rather, so then I get d alpha wedge beta j plus, well here I'll be, now this omega is right, so here I'll be getting a negative sign actually, because the first term here is a one form, negative of, then alpha wedge d of beta j. Now alpha is of the form daj. So d alpha will be where aj is just a function here. That's what we started with, and we already seen that for so in other words a zero form. So we know that by the what we just did here, k equals 0 case, that will tell us that d alpha is d of aj is 0. So the previous step implies that this term goes away and you're just left with negative j alpha wedge d beta j. And one just has to check that each for every multi-index j, d beta j is 0, and that's quite easy because d beta j, after all, what is it? This is d of, again it's one just keeps on applying Leibniz rule. So one can check that basically one will keep on getting, see, one will end up keeping all these one forms fixed and taking d of one of the in between ones. Of course, one has to start with the first one and so on. And then it will just, what the sign you will acquire will depend on how many forms will precede that. So therefore, you can write this as -1 to the power I. And then, right, so d of xj1 wedge, you have to basically, you will end up taking d of xji. So here summation is over I dot dxjk. So for instance, when I do the first one, I'll just get -1 to the power -1 basically. D of this, actually here, yeah, it should be, maybe I should change it, the index to I plus 1. I think that will be fine. So, or I might, yeah, let me write it as I minus 1, that's more clear. I minus 1. And then, yeah, that makes sense. And then, right, so one has this, and in the end, basically one is again using this fact that if you have a d of a one form, d of a function rather, then that will be 0. So the previous step. So all these things are 0. So essentially using the previous step, one gets it for all k. So, but ultimately the fact that d composed with d boils down to the fact that mixed partial derivatives are equal. So that proves d composed with d is 0. Now let's move on to the next one, which is the last one, which is the fourth one is f star d omega equal to d f star omega. Here f is a smooth map between two open sets in Rn and Rm. They need not be in the same Euclidean space. Right. So again, enough to consider forms omega which are just a function times dx. So here I am pulling back a form on V, so this u will be a function on V. And the reason it's enough to consider forms of this type is the usual reason, namely any k form can be written as a sum of such forms. And in this, what we are trying to prove in this expression, if we plug in, so basically it's both sides are linear in omega. So therefore, if it's true for certain omega 1 and omega 2, the equation will also be true for omega 1 plus omega 2. Therefore, we can just restrict ourselves to forms of this type. So let's look at the left hand side. F star d omega star u dxi, and this will be f star, again Leibniz rule, du wedge dxi plus, now here I'll get -1 and then u times d of dxi, which we already seen is 0, so I won't even write it. So the second term will be 0. So I'll just get this, and well, what is this? So this is f star du wedge f star dxi now f star du is, it's quite straightforward to check that. If you, f star du is the same as d of u composed with f, and one can see this just by acting it on a tangent vector v. Well, what is f star du after all? This by definition is du acting on df of v, and this is the same thing as du composed with df of v, which is du composed with f of v by chain rule. So therefore one has this. So this is d of u composed with f, well, I don't have to write the v here, wedge. Now as for this, remember that dxi was dxi1 wedge dxik, and we know that f star, the pullback, behaves well with respect to exterior multiplication. This has nothing to do with manifolds or smooth maps. This was just came from the multilinear algebra that we talked about a few lectures ago. So when I do f star dxi, I get f star dxi1 wedge f star dxik. Okay, let me write that a bit more clearly. So this is f star dxi1 f star dxik. So I'll have these things, and also let's from what we just this thing here, this is the same as d of xi1 composed with f, etc., d of xik composed with f. So what I end up with is dxi1 composed with f dot 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 dxik composed with f. So this is the left hand side. Now let's show that the right hand side leads to this exactly the same expression. Well, f star, I have to start with f star omega, and I go back to this expression here. So this is f star, so this is a 0 form and this is a k form. So this is the same thing as f star u. Here the times f star dxi. This is the same as the pullback of a function. It's u composed with f multiplied by, again, f star dxi. Well, I just use the same expression that I have here. I use this expression for f star dxi. And then, so this will be d xi1, oops, not quite dxi1, dxi1 composed with f dxik composed with f. Well, essentially I end up with the same thing on both sides. Now, not quite, we are not yet done, so I have to take d of this. So d of f star omega. Now, again the same thing. So when I have to apply Leibniz rule, k times, k plus 1 times actually. So, but all this, when I take d of this other terms, d of any of these terms, this and anything in between, I'll end up getting 0. So Leibniz rule just gives me two terms. One is d of u composed with f wedge d of xi1 composed with f. Well, actually it gives me just one term which is non-zero, which is this. So I am just differentiating the function. So, and this, if one compares, they are the same. So we have proved that pullbacks behave well with respect to exterior differentiation. So once we have this in hand, now we can, this completes our discussion for exterior forms in Rn. Now we can move on, go to manifolds and prove the main result, which is basically the existence and uniqueness of this D operator. So now let's recall what we were trying to prove. The theorem was that there are unique linear maps D from omega k m to omega k plus 1 m. So here k varies between 0 and, well, if the dimension of the manifold is n, we know that any n plus 1 form, or basically any k form where k is strictly greater than n will be 0. So I might as well say that k less than or equal to n minus 1, because here I have written k plus 1. There are unique linear maps such that df, so for a 0 form, and we have the Leibniz rule. Yeah. D omega wedge eta plus minus 1 to the power k omega wedge theta, where if omega belongs to omega km. Third one is d composed with d is 0. So we also have additional properties which satisfied by d, but these are the three main things. The additional properties are consequences of these. Well, not quite consequences. The way they are constructed, the additional properties will follow. The uniqueness just follows from these three actually. So let's stop here. We'll resume from next time.